Okay, so this is a small activity to demonstrate the concept of resonance, right? So when buildings are subjected to ground motion at their base, if the nominal period of ground motion matches with that of the structure can undergo large vibrations, and that is referred to as resonance, right? So we have made two simple models of, you can say, buildings, or they are more like 2D frames, okay, and they are made from locally available materials, right? So for instance, these are made of erasers, right, and we have put these button magnets basically opposite parts so that they can be easily assembled, okay? And so both of them are nearly of the same mass. However, what I have done is I have wrapped some sellotape around these vertical members to make it slightly more stiffer in comparison to this one, okay. And so what we are going to do is we are going to start oscillating the base first with a very small frequency, and then we will gradually increase the frequency. And so when the frequency of oscillation of the base is going to match with the natural frequency of one of these structures, that particular structure is going to start undergoing high, it's going to start undergoing vibration with high amplitudes. And the structure to my left, because it is more flexible, it has a smaller natural frequency, and therefore this structure will end up being excited first, right? And once we increase the frequency beyond this structure's natural frequency, then it is this structure which is going to be excited at a particular frequency of oscillation. And so we will try to capture this effect now, okay. So first I will start with a very low frequency of vibrations. So both the structures are hardly undergoing relative displacement with respect to base. Now I am going to increase the forcing frequency, and you can see that the structure on my left has started undergoing larger, vibrations with larger amplitudes because it is more flexible. Now if I keep increasing the frequency, apparently around at this point it is in resonance. So this is the time period of base motion is matching with the time period of the structure. Now let me increase the base frequency a little bit more, okay. And so now you can see the right structure has started undergoing large vibrations in comparison to the left, right. In fact, it has actually come off, right? And that can actually happen in a structure, right? If it undergoes very large vibrations, you can have large deformations, failure in some members. Here it was more of a mechanical failure, but still the point remains that we should be wary of this phenomenon, right? So this is the frequency at which the right structure is resonating, and the left one is not undergoing that much vibration, right? And now when I am going to increase the forcing frequency at the base beyond the natural frequencies of both these structures, right? So what you will find is that neither of these structures are undergoing resonance, and in this case, the response is therefore not that high, right? In fact, it can be shown that when your frequency is much larger than the natural frequency, then in this case it is mostly governed by the displacement of the base, okay. So this mass will remain stationary, it is only the base which is going to move, and so that is what is precisely happening. In an absolute frame of reference, the mass at the top or the beam at the top is going to be nearly motionless, okay? And we are not able to replicate it perfectly because I am not able to produce a consistent frequency high oscillation at the base, okay. Let me try with one hand maybe. Right. So now maybe we can observe this effect.